This conference will now be recorded.
So very good evening, students. Today I will be discussing numerical problems and analytical problems on modern physics, where we are taking questions from the chapter Photoelectric Effect, Semiconductor, Atoms and Nuclei. So these questions which I am taking today, these are all from previous year JEE mains paper. So the very first question is from JEE paper 2004. So let us read the question and try to solve it. The figure shows the variation of photocurrent with anode potential for a photosensitive surface for three different radiations: IA, IB and IC be the intensities, and FA, FB and FC be the frequencies of the curves for the curves A, B, C respectively. So there are three different radiations are used for photoelectric effect, and three different radiations has three different intensities: IA, IB and IC, and each of them has different frequencies as well. For this particular radiation, frequencies is IA. For this particular radiation, the frequency is FB, and for this particular radiation, the frequency is FC. So in this figure, what is plotted? So this side photocurrent and this side the anode potential. You have to answer which of these four options will be correct. Look, these three figures, like three graphs, A, B and C. You can see the photocurrents are same for B and C. Photocurrents are same for B and C, but not for, this is like photocurrent for A is not same as these two. Another important fact you can see, the anode potential in the negative side, this is significant, and this, where the photocurrent becomes zero, that particular potential is called stopping potential. Okay, stopping potential. So this is one stopping potential. Suppose this is V1 and another one is V2. Okay, so this stopping potential is same for A and B. You can see that the negative potential at which the photocurrent becomes zero is called the stopping potential. Okay, and stopping potential for B curve and A curve, or for the radiation B and A, is same, that is V1, and this is less compared to the V2. So here let us now look the options. So in the first option it is said FA is equal to AB. That means the frequency of the radiation A is equal to the frequency of the radiation B. That means the frequency of the radiations A and B are same, whereas the intensity of A is less than intensity B. We have to see how does photocurrent vary with the frequency, with the frequency and with the intensity. At the same time, you have to see how does the stopping potential vary with the frequency and intensity of radiation. So we'll just see these 2 points, that photocurrent we know this very well. Photocurrent is directly proportional to the intensity. Photocurrent is directly proportional to intensity, but stopping potential does not depend on intensity. Does not depend on intensity. Okay. And third point is that the stopping potential actually depends on the frequency of the incident radiation. Stopping potential one more point I should write: photocurrent does not depend on frequency. Photocurrent, in the sense, magnitude of the photocurrents, obviously it depends somewhat on the incident frequency, because if your incident frequency is not greater than threshold frequency, then at least greater or equal, then it cannot be, a photocurrent cannot be obtained. So not in that sense I want to say that the variation of photocurrent doesn't occur or doesn't happen with the intensity, frequency. Photocurrent does not depend on frequency, depend on frequency. Okay, so the last point is the stopping potential depends on the frequency of the radiation used. Radiation, or let us say incident radiation. Okay, so in this case, look, if the stopping potential is same for B and A, then what we can say? We can say that frequency of B and A radiation will be the same. It is obviously the stopping potential V is directly proportional to the frequency of the incident radiation. Okay. So this is one. And another one is that the intensity. See, these are two different currents. So, but this case, you look B and C, they have the same current value. That means that intensity is same. And in this case, you look, if I say this one is true, then I have to see this IA intensity is less than IB. This is true, right? In this case, at least I can say IA is equal to, IB is equal to IC. IB is equal to IC, but nowhere that option is given. Okay, so I have the first option, which is correct. FA is equal to FB, because the total potential for both B and A radiation is same. and the current due to radiation A is less than the current due to the radiation B. That's why I can say the intensity of the radiation A is less than the intensity of the radiation B. So this is how we can analyze and solve this problem. Okay, so I have option A correct here. Now let us see the second question. So this question says, after 280 days, the activity of a radioactive sample is 6000 dps. We know activity is written as R is equal to R0 to the power minus lambda into T. So this T is given as 280 days. Activity reduces to 3000 dps after another 140 days. Okay, after another 140 days. Initial activity of the sample is 6000 dps, 900 dps, 3000, sorry, 9000, 3000 or 24,000. What is the initial activity? That means you have to find out this value. Initial activity. Okay. Look, there is a clue over here. The activity in 280 days, it is 6000. So 280 days decay, see, activity is 6000 dps and another 140 days it is becoming like this. Okay, that means, you know, in this case, you look, the disintegration is happening half of the nuclei, exactly half of the nuclei, half of the nuclei decays here. Okay, that means activity is becoming exactly half. Activity is becoming exactly half in 140 days. Sorry, 140 days. That means what is the half-life? Therefore, we can say half-life for this particular half-life for this radioactive sample is 140 days. This is half-life. So then you can see how many half-life. After how many half-life it becomes 6000, 2 half-life, because 180 or 140 into 2. So here before, then you have to find out initial, if you want to find out initial activity before 2 half-life, half-lives the the activity was that will be the initial activity. The activity was 2 to the power 2 into, actually it should be 2 to the power n half-lives into 6000. So this would give you 24,000. So this will be the answer. So here actually, where the sample disintegrates, radioactive sample disintegrates to like yes. So in 280 days, radioactive decay is happening. 60,000 dps, the activity of the same sample is reducing after 140 days. The initial velocity, sorry, initial activity, the sample will be 2 to the power 4 into 6000. That will give you 24,000. Okay, so this is the activity of the sample in dps, initial activity of the sample in dps. Okay, all right, we'll go to the next question. So this question says that an electron in a hydrogen atom first jumps from the third excited state to the second excited state, see the hydrogen atom, okay, and subsequently to the first excited state. The ratio of respective wavelength lambda 1 to lambda 2 of the photons emitted in this process is, so let me explain you once again. So this is ground state, n is equal to 1, or I should say E is 0, here E 1, n is where n is equal to 2. Okay, so n is equal to 3 over here, n is equal to 2, that is the first excited state, n is equal to 3 is the second excited state, n is equal to 4 is the third excited state, third EX state, excited state. Okay, let me just keep that as EX3 itself, excited state. Then n is equal to 3 is called second excited state. This is first excited state. And this is ground. Excited state. Okay. U1, this is E2, this is E3. So here the question is that the hydrogen atom, electron in a hydrogen atom first jumps from 3 to like from third excited state to second one. So this is 1. So this corresponding wavelength is lambda 1 because the excess energy will be released as photon. So and subsequently it is de-excited to the first excited state. So that is n is equal to 2, and this corresponding radiation has wavelength lambda. So we have to find out the ratio of that. So we know that wavelength 1 by lambda is equal to R into 1. R is the Rydberg constant. Okay, sorry, this is our n, sorry, n final, n initial. N initial square. Okay, now see, if I put the values, see, n for this particular wavelength 1 by lambda 1, R is constant. What is the final set? See, n is equal to 3. So 1 by 9 minus coming from initial state this one. So 1 over 60. So it will be 7R by 9 into 16. Similarly, I can write 1 by lambda 2 is equal to R into, see, lambda 2 means it is going to n2, that means 1 by 4 minus coming from, so this is 5R by 36. So if we take the ratio, we have to get lambda 1 by lambda 2. So then better let us do this. So this is 9.4 and 1 over lambda 1 is, see, 1 over lambda 1 is, so here you have to write 7R divided by this, it will go up. So this will be, see, 20 by 7R. Therefore, the first option will be the correct answer for this question. Okay. Now, let us move on to the next question. This is also again a very interesting problem. To solve it, so this question states that in a photoelectric experiment, the wavelength of light incident on a metal is changed from 300 nanometer to 400 nanometer. So in a photoelectric experiment, the wavelength of the light incident on a metal is changed from this to this. The decrease in stopping potential close to what among these? Okay. So here, let us write the, so this is also from photoelectric, and this problem is from 2019 JEE main. So let us write the Einstein's photoelectric equation. So what is that? Einstein's photoelectric effect is given, photoelectric equation is given by h nu is equal to phi or in other way I'll write the maximum kinetic energy with which photoelectrons emit will be exactly equal to h nu minus phi. Phi is the work function, and this is the radiation, like energy of the incident radiation. So this kmax can be written as electron volt E into V if these are converted into electron volt. Okay, this h nu can be written as Ac by lambda. Okay, and this, suppose this is phi in electron volt. So now we can write this in the modified format, phi like this. Okay, or we can do one thing, we can just okay, so we have been given some number here like this. Okay, we'll just see. All right, so we have a modified format of the photoelectric equation given by Einstein, that can be written as C by lambda. This will be plus, okay, hc by lambda is equal to E into V plus phi. Phi is the work function. Now I can write this equation for two different wavelengths. I can write this for lambda 1, okay, lambda 1. So the stopping potential will be different, okay, for different wavelength, but the work function remains the same. So I can write this is EV2 plus phi. Phi is the same for both. Now look, you have to find out the difference in the stopping potential. So I can just take the difference from both sides. Okay, both sides I can just take, subtract, or I can write subtracting equation 2 from equation number 1. What we will get? AC by lambda 1 minus AC by lambda 2. So I'll take AC common, AC common, 1 by lambda 1 minus 1 by lambda 2 is equal to E into V1 minus V2. Okay. See, when the wavelength is less, frequency will be more. So that's why V1 minus V2. Okay, or 1 by lambda 1 minus 1 by lambda 2. So here we can do one thing. We can write this V1 minus V2 or delta V, change in the stopping potential is equal to Hc by E 1 by lambda 1 minus 1 by lambda 2. Okay, so this is the change in the stopping potential. I'll go to the next page. Okay, I haven't kept any space. In the next page, let me, I hope these equations are fine, but still, okay, let me just make use of this particular portion. So see, this delta V can be written as AC by E. Now let us AC by lambda, sorry, ACE, this can be written as thousand 240 nanometer. This particular thing has value. Nanometer electron volt or nanometer volt, and this is 1/300 minus 1 by 400. Okay, So what we'll get from here? This 0 is also there, minus. Okay, let me just clean this question. Here 100 by this, and these are actually 1 over nanometer here. So nanometer will actually cancel it. This 2, this 100 will be of nanometer. So here it was. Okay, so this will be 10 to the power 4 here. So there will be another 100 over here. Okay, so you have got this in volt divided by, so this 10 will go up 120. Okay, so this will be nearly equal to 1. So this will be nearly equal to 1.0 volt. Now we'll go to the, so here the question answer is this one. We'll go to the next question. So this question says that the stopping potential V0 in volt as a function of frequency for sodium emitter is shown in the figure. So in this figure, this is the V and this is the frequency. So here stopping potential is plotted against frequency for a sodium emitter as shown in the figure. The work function of sodium from the data placed in the plotted in the figure will be given So let us just try to understand once again the problem. The stopping potential in volt is a function of frequency for a sodium ion is shown in the figure. The work function of sodium from the data plotted in the figure will be, so you have to find out the work function from the plot actually. That is the question. So what is the question? The question is that you have to find out the work function of the material, okay, or metal used here. So look here in this potential, stopping potential, this plot, we have to actually let us first do one thing. In the previous question, we know what is stopping potential, right? Stopping potential EV is equal to hc by lambda this is the phi, and this is here actually this is stopping potential hc by lambda e. So if we plot it against, okay, this can be written as even h nu by c, sorry, h nu by e. Now you have to find out work function, right? So what will be the work function? Work function is this one. So you have to actually take negative, it's negative. So this will be the intercept actually, okay, the intercept. So work function will be from here, if you want to find out, work function will be actually the intercept. Y is equal to, this is a linear curve, y is equal to mx plus c. So x is nu. So if we plot this stopping potential as a function of frequency, then slope will give you actually this. The slope will be given by h by e. What is the intercept? Intercept will be gives the negative potential, or sorry, this is the work function. So in this case, you look what is the thing. This is 1. It is becoming 0 over here. So what would be the answer for this question? You have to see from the graph and decide what will be the answer for this. So you have to find out the intercept here to get the answer. What is the threshold frequency? Here it is threshold frequency is this much, around 400. Okay, since the graph is not very prominent, like there are graduations which are not proper, we would have got from the graph itself, but then we have to check with this equation, and let us see how we can do it from the equation itself. Okay, so few things are given here. This is H is given, fine. Here actually one thing you can just see from the graph, what is the work function? Work function actually will be nearly equal to, or it should be exactly equal to the threshold frequency. Threshold frequency. And what is the threshold frequency here? Threshold frequency is this much. You can see that. So from there you have to find out work function. So work function is equal to phi is equal to h nu 0. See, if we would have got the intercept, then you would have got from directly from intercept itself with multiplying E into V0. Okay. But in this case, the intercept is not prominent, so you have to go with this. So nu 0, this is threshold frequency. So 4 into this scale is 10 to the power 4 hertz. So h, you know, this 6 into 6, 3, 10 to the power minus 34, and nu is 4 into 10 to the power 14 hertz. So this will give you the energy in joule. Okay, energy in joule. If you want to get this in terms of electron volt, then you have to divide this particular numerator with 1.16 10 to the power minus 19, and that's how you will obtain the frequency. If you just solve it properly, let me just so what are these? 10 to the power minus 34 plus 19 plus 14. So this will be 6.634, and this there will be 10 to the power minus 1. 10 to the power minus 1 means divided by this 4. So if you divide this 6.63 with 4, what you get? Sorry, this will be 6, 24. This will be another 5, 1.65. So around this, then electron volt, and this will be nearly 1.66 electron volt. Okay, this is how you can find out work function. So this was also a good problem, and this problem is also from 2019 JEE paper, May 2019. Okay, with this we'll stop it here for today. We'll continue another 1 or 2 more lecture with this, because there are many more questions. In fact, this modern physics part is important for JEE advanced questions. So we'll try to pick up a few more questions on this modern physics part in next 1 or 2 lecture. So thank you for your patience. Bye for today.